So this is limits number 5. It's our last new limits lesson before test review, and it's not going to feel brand new. It's kind of a compilation of graphical limits and the discontinuities and the definition of being a continuous function or not. So at the top, we have some very specific definitions for you. A function is continuous if at an x equals a, the limit at a is the same as the y value at a. If a function is not continuous, it can have two kinds of discontinuities, removable and non-removable. In the past, removable we've called a hole. I know that pen doesn't work. Removable we've called a hole. Non-removable would be a jump or a vertical asymptote. And last year, we called vertical asymptotes infinite discontinuities. So the definition of a removable discontinuity is that when x is a, the limit exists, but the y value at a does not exist, or the y value is not equal to the limit. So if we look at number 1, this is going to have a removable discontinuity, and here's how I know that. The numerator factors, and one of the factors divides to 1 and leaves us with just x minus 5, which is why you see a line as the graph. So when x is negative 5, this point right here does not exist because you can't divide by 0. So when x is negative 5, that makes a case where you divide by 0. This would be a removable discontinuity because the y value at negative 5 does not exist. There's a hole there. So if we fill in our limit statements, as x approaches negative 5 from the left is this way, this y value is right here. So there's two ways to get that. If you don't have a graph, you could put negative 5 into this reduced equation, and we get negative 10, or we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The limit at negative 5 from the right, negative 10. These are the same values, so the limit does exist, but the y value at negative 5 does not exist, creating a removable discontinuity. So example 1 has a removable discontinuity at x equals negative 5. F of negative 5 does not exist, but the limit as x approaches negative 5 does exist and is equal to negative 10. If we define f of negative 5 to be negative 10, I'm just going to choose the non-existable y value to equal the limit, then we would fill in that hole, we would remove the discontinuity, and the graph would be continuous. A non-removable discontinuity is a jump or an infinite, which is also called a vertical asymptote. So x plus 3 over x minus 3 has a vertical asymptote here at x equals 3. I know that because 3 is what makes the denominator 0. So the limit as x approaches 3 from the left is going to negative infinity. The limit as x approaches 3 from the right is infinity. These are not the same, so this limit does not exist, and there is no y value at 3. All right, on page 22, we have a jump discontinuity, and there is no value here at negative 3. Those should be open holes because we can't divide by 0. So the limit as we approach negative 3 from the left is this y value of negative 1. As we approach negative 3 from the right is the y value of positive 1. Those are not the same, so the limit from both sides does not exist, and there is no y value at negative 3. This graph also has holes here at 2. So as we approach 2 from the left, the limit is -3. 2 from the right, 3. Both sides, that does not exist. And there is no y value at 2. So then your homework is page 23. And the top is just restating what we just went through, but then here's the directions. Graph each function, so you can use your calculator. Determine, examine the function for continuity. Determine if there is a discontinuity. If so, is it a point, jump, or infinite? So there's 3 parts. Determine if there is a discontinuity. Part B is what kind. Part C is state the x value where that discontinuity occurs. And if it's a point discontinuity, like the hole, determine if it's removable and give the xy coordinate that would remove it or plug in the hole. So I'm going to do numbers 1 and 2 with you. To find out any values where there is a discontinuity, what we did earlier in the unit is we said the denominator equals 0 will cause a discontinuity because you can't divide by 0. So let's factor this. So you get x equals 3 and x equals 1 as a discontinuity. So if I rewrite these factors aren't the same, so they don't eliminate. I think these will both be asymptotes since nothing eliminated, but let's check. I have a 86 calculator here at home and it works a little differently, so it gives me a second to figure out the right buttons to push. Okay, so when you go to type your function in, you need parentheses around the numerator and parentheses around the denominator. And I'm going to type the original problem because that way I don't have to trust if I factored correctly. And then we're going to graph it. Okay, so sure enough, there's my vertical asymptotes. Your sketch here doesn't have to be perfect. We just want to get a sense of what the graph looks like. So when I go to graph these pieces, I'll do the curve, the kind of parabolic shape, and then the curve. So it's like this, and then like that. So, okay. X equals 3 and x equals 1 are the discontinuities. They are infinite, both of them. And that's it. Okay, number 2. There's nothing to factor. The denominator equals 0 at 7. 1, 2, 3. That's here. So then let's see what that looks like in the calculator. If you're looking for absolute value, if you hit the math button, oh man, where's the math button on this one? If you hit math and arrow over to num, oh, here's mine. There's num. ABS stands for absolute value. Oops. And if you look back at the class examples, when you had the absolute value divided by the non-absolute value of the binomial, it was a jump. So let's see what that looks like. So we've got this horizontal segment to 7. And now my calculator tries to combine the jump discontinuity. You have to be wise enough to know that it's not connected. You have the brain, the calculator does not. So if you hit trace, here we go, and arrow along your graph, or you can hit trace, negative, positive 7, enter. You'll see there's no y value. But if then I go a little bit to the right, now I'm up at positive 1. A little to the left, I'm at negative 1. So this is a jump discontinuity. And there's the answer for number 2. So your homework is to finish page 24. All the answers are already in Drive for you to check. Down here for 7 and 8, these are unique. This symbol is the greatest integer function. So again, in your calculator, if you hit math, num, like arrow over to num, and it says int. And these are the step functions. Back in the beginning of the year when we graphed it, it looked like this. But this 2 and the 1/3 will make the scale a little different for you to look at the graph.